Hello, December 26th, 2023. I don't think I'm quite well these days. I'm been sleeping like 9 to 10 hours every night for 3 nights now. I do feel fresh, sort of, but well, we'll see how it goes. I thought I would try it. Actually, when I read this problem, I thought, well, isn't that obvious? Because we have proposition 30 that it lies in M1 of 4 point chi, with this giving plus minus 1. So if we, and that's for, I'll just write it. So if we have a gamma in gamma naught of level 4, then it's chi of d gamma squared. And that means if we square it, then this equals unity, so it just gives. So this seemed trivial to me. I hope I'm not mistaken here. Well, then we must find the values at each cusp. And as far as I remembered, the cusps were infinity, of course, a naught, and 1/2, or minus 1/2, whatever you want. And I just got my document with the subgroups, the congruent subgroups we've been working with, and that's minus 1/2, naught, and infinity. Right. So they were right. Oops. The value at infinity is obviously unity. And to find the value at naught, we use the matrix S. Which maps infinity to naught. Now let's see, that's set to minus second, phi to the 4th minus 1 divided by z. And that's where we must use 2, 5. So we need to put this to 4th power. And that means this squared, and minus squared is minus 1. So it's minus 1 divided by 4z. And to get this, well, what's the easiest thing to do? we substitute z with z fourth and multiply with this on both sides. I don't like that. I expected z squared, really. So it's z, the square root of z to fourth, that's z squared. There we go. There should be a minus here as well. Meaning that what we have here equals that from the other side and then that. So we are left with z to fourth of z fourth. And that means that it would be 1 plus, and then this to the fourth. That's quite a lot. That's q times 4, that 8q. And I believe the next term comes from 4 times 1 to the third times this. That's 8q to 9/4, etc. Meaning the value, that's a poor choice of color, really. Equals unity as well. For 1/2, infinity maps to 1/2. We can just do like this. Well. So in this formula we substitute z or this is what I'm talking about. It should be quite easy to choose either to substitute z for 2z plus 1, or so what am I thinking about really? I just got stuck. Oh, actually there is a problem. Let's substitute set by what we have in here. There we go. Then these two will cancel. And we get, isn't that blue? No, that's black. Minus 1/4 side 4th of minus z halves plus 1/4. And this, of course, goes like 1 plus. This will actually be an infinite series of negative powers of z. Which is most unfortunate. I'll just make a break. That's a very simple computation. We've done it before. So I'll just find the error and correct it, and then we can start on problem B. Good morning. It's 6 o'clock. But, well, I awoke and don't fall asleep again. I did make a recording yesterday, but it was without sound, so I'll just repeat what I did. First, I looked this over, and as a teacher I could find many mistakes. Here we forgot n equals 1. It gives 2 cubed first, and down here that would be 8 times q to 1/4, 1/4. And we get an extra term there. Then I forgot to write the result here. This one we haven't found yet. What I had done down here earlier, I think is the wrong way to do it. Not that we can't come through, but I'd rather do something else. You see, I read the proof of proposition 30, where they used some matrix magic, so I thought I would do some matrix magic of my own. But there was a worse problem. Here we've got it. To finish the proof of the proposition, we must show the cusp condition, and it will be shown in problem 11, and what will be shown is exactly this. And they use this to show that the limit is z turns to I infinity of these guys all are finite. They say they are bounded, but I'm not I can't prove that that's sufficient, but I believe that if the limit is bounded, then we are home. So I wanted to do some magic of my own, and I tried playing a little with this gamma, operating with alpha from both sides, and then we actually got the matrix 1, 1/2, 0, 1, which is the translation by 1/2. So that means that we can write gamma this way. And that looked promising. Oh, it's not really necessary, that's silly, but I put alpha over on the other side, and I haven't written here what alpha is, so I better. And then t, the minus does nothing, because we are in k equals 2. T to 1/2, that's just the translation. And then we have to operate with alpha on this. Now, I thought a little about this, and it changes sign on all the odd powers of q. So it's 1 minus 2q plus 2q to 4th minus 2q to 9th. And I thought, well, that seems like we have some difference with theta of 2z. And then I checked the previous problems and realized that problem 8a, we proved this formula. So it was actually theta of 4z. Probably having to do with the squares here. Well, so we apply this. And then I thought to have k being unity, we need to look at the square. But this morning I said, well, let's open our minds, and this is the translation formula for theta. And why must k be an integer here? As long as we are in the branch with the natural logarithm, where something to a positive real power, it needed to be positive, well, to a real power, 1 to a real power is unity itself, I think we are fine. So there's no need to let k only be integers. I'll now write this formula using k equals 1/2. So it's the same gamma. And the determinant of gamma equals 4. So the determinant to 1/4, that's square root 2. 4z to minus 1, that's minus k minus 1/2, theta of minus 1 divided by 4z. To minus 1/2. And now we can apply this formula. So it's I to minus 1/2 theta of z. And we have a functional equation here. If we have f of z k1 times g of z, the same gamma, but another order, then it's actually f times g of z to k1 plus k2. So it's some kind of graded algebra. I don't know exactly what the structure is here. And that means that we can simply take the interior here and operate with alpha of order 1/2. Now I'll do it correctly. F of z equals, and what we need is f to the 4th gamma 2 so k is 1/2 here, and then put that to 4th. That was my idea. So let's try that. First, the determinant of... Oh, actually we can do it one by one, can't we? No, we only have theta. So maybe we should do let's do this by itself. So it's the same as above. Square root 2 4z to minus 1/2 theta of minus 1 divided by z. And now it's time to use this with substituting z divided by 4 for z. This gives 1 divided by square root. One thing. So z gets substituted with z divided by 4. So this is just z. No, not in that formula. My God. So this is divided by square root 2. So they cancel. Z to minus 1/2. Now we start with what we should. Now we start applying this formula. So this is just reduction. 2 times z 4th minus 1/2. Oops, that must be put on the other side, so it's plus. Oh, just theta of z 4th So they cancel. And we end up with 1 divided by 2I and the square root of that. And it's a factor 2 to it when we go up here, so it's the square root of 2 divided by I, theta of z fourth, minus theta of z to fourth. I'll just check that this is correct. Minus 4 square root 2 q fourth, etc. So this should be the value at minus 1/2. That was, it was plus 1/2, but it's translation invariant, so it's the same. Well, I went through it once more, of course on a new sheet of paper. It's the only way to find the mistake. And this was the problem. They don't cancel. And that means that this gives naught. So the expansion I got to the fourth was naught minus 8q4 plus 12q4 squared, etc. Oh, minus. Meaning the value up here vanishes. Actually, I don't think the way I did it was too complicated, but maybe we can use the method of chapter 2 on this guy, going back to the theta function, 2x squared, and then using Poisson's formula on that to isolate the even terms. Actually, I like this way better.